Okay, great. Thanks so much to everybody for being here. It's really an honor to be invited. I love this series, and I'm a huge fan of many of the people in this audience, including perhaps especially those who will disagree with me. It's really great to see all of you here. I'm excited to hear your comments and criticisms, and so thanks again. So I'm going to be talking about Everettian quantum mechanics, particularly how to understand probability in Everettian quantum mechanics. And so I'll be talking about branch counting. I'll be proposing a kind of a new rule for how to think about branch counting. And I'll try to defend that rule and talk about how it conflicts with the Born rule and argue that if some of the defenses I give of branch counting work, then this poses at least some additional challenges for how to understand probability in Everettian theory. Perhaps nothing decisive, but at least moves some of the debate forward. So, and then I'm going to talk about some common criticisms of branch counting, especially having to do with the idea that there is no such thing as a number of branches in Everettian theory. Try to respond to that concern. And then finally, I'll address a really interesting and novel proposal from Simon Saunders, who's here, and offer some sort of preliminary concerns about that approach, and see if we can make some progress. So anyway, so what is Everettian quantum mechanics? Most of the people here probably already know, so I'll say very briefly that Everettian quantum theory essentially says the universe is completely described by a wave function evolving unitarily according to the Schrodinger equation. So the theory posits no so-called hidden variables, such as the kinds of the particle positions that you see in pilot wave theories. And it does not postulate that the universe ever fails to evolve to evolve according to the wave function. There's no collapse. There's no probabilistic collapse of the wave function. And the kind of Everettian analog, or you might say replacement for collapse, is the idea that upon measurement of some quantum system, rather than the wave function collapsing to one or another determinate eigenstate of the observable you're measuring, instead, the universe sort of branches into multiple copies in which different results are instantiated. And I think it's really important to say, in fairness to defenders of Everett, that these branches are kind of emergent patterns in the wave function, that branching does not do anything to influence the underlying dynamics. They're not additions to the fundamental ontology. They're something that are sort of thought to follow naturally from the theory in conjunction with some assumptions about how we get emergent ontology from fundamental ontology. A lot of really interesting work has been done recently and is ongoing about that question. So the sort of everybody's favorite thing to worry about when one worries about Everettian quantum mechanics is to say, look, quantum mechanics gives us these probabilities that when we perform measurements, we will get one result or another. And if you're telling me that every possible outcome is instantiated on one branch or another, what could you even mean when you say that there is a certain probability of getting this or that? And this is important because a very central part of the edifice of quantum mechanics is the Born rule, which says that when you perform a measurement on some observable O hat, the probability of getting some eigenstate alpha for a state, written as here in an eigenstate of a basis of eigenstates for that observable, is equal to the squared wave function amplitude corresponding to that observable. When you're dealing with continuous observables, you integrate over possible values of that observable. But for now, this should work. So you might worry about two different kinds of problems for probability in Everett. One is what's been called the incoherent problem, where you ask, what could these probabilities even mean in the first place? I mean, isn't it the case that in Everettian quantum theory, every possible measurement result actually does occur with probability 1 on some branch or another? So what do you even mean by probability? And there's also the quantitative problem, which is essentially, if you hand me some or another way of understanding probability in Everett, why is it that the probabilities that we get are the Born rule probabilities? Why is it that the squares of the wave function amplitudes give us the right probabilities and not, something else? So this paper is mainly focused on the quantitative problem. And I'm going to assume that the incoherence is basically solved by the idea of self-locating credences, self-locating uncertainty. The rough idea being that, if you branch into multiple successors on different branches, you might know exactly what the quantum state looks like. You might know exactly what the branching structure looks like up to precision, or up to the degree to which that is precisely defined. But you don't know where to find yourself in the Everett verse. You don't know which branch you're on, and you can be uncertain about that. And so when I ask, what's the probability that I'm going to see spin up or spin down, I'm really asking, am I on a spin down branch or a spin up branch? And I don't know. People have raised concerns about that, including many people here, but I'm going to just assume that this problem is solved and focused on the quantitative problem. So when one thinks about the quantitative problem, something that kind of very naturally comes out is to say, okay, sure, I can be uncertain about which branch I find myself on, but if I could be on any one of n possible branches, assuming that they're a finite number, shouldn't I just be equally uncertain about being on any one branch or another? In other words, shouldn't I adopt this principle that I've called naive, or that David Wallace calls naive branch counting, which says that if your evidence is consistent with being on any one of n branches, and m of those branches realize some eigenstate alpha, that then your credence that you're on an alpha branch should be m over n. But this rule is going to conflict with the Born rule so long as you don't think that the numbers of branches covary with the quantum state. So that's certainly a problem for Everettians. And so Everettians often want to give us some independent reason that branch counting is not going to work. So here's one such independent consideration against branch counting that David Wallace offers. So imagine you're in some state, which is just a superposition with whatever amplitude you like of spin up and spin down. And you have some device which registers the z-spin of that particle. If the system evolves unitarily, according to the Schrodinger equation, rather than collapsing, as it happens in Everettian theory, then the combined spin particle plus device system is going to evolve into a superposition of the particle being spin up, device saying spin up, plus particle spin down, device saying spin down. So now imagine that in such a setup, you measure the spin of that particle at some time t1. This induces a branching event, and then you observe the results at t2. And if and only if the result is spin up, you perform a similar experiment on a second particle in the same initial quantum state at some time t3, and you observe the results at t4. So here's kind of what that branching structure might look like. So there's a first branching event, splits into up and down branches, and then a second branching event only on the initial spin up branch into two more branches. And now you have, and this is a major simplification of the actual branching structure, but you have three branches. And naive branch counting seems to suggest that at time t2, when there are two branches, you should be, you should have credences of 1/2 and 1/2 in the two possible results of the initial spin experiment. But at t4, now there are three branches, two of which had the first particle to spin up, one of which has it as spin down. And so you should assign credences of 2/3 and 1/3 to spin up and spin down for the initial spin measurement. And this seems to be a kind of diachronically inconsistent way of setting your credences. The problem is that this violates a principle that I'll call diachronic updating, which essentially just says that your credence in up at t4 should just be a kind of a mixture of your conditional credences in up at t4 given up at t2, weighted by your credence in up at t2, plus credence in up at t4 given down at t2, weighted by your unconditional credence in down at t2. And this, of course, is violated by naive branch counting, which says that no, at t2, your credences should be like this. At t4, they should be like that, and they do not depend on this in this normal updating way on each other. And so what this seems to show is that if we're going to formulate a reasonable branch counting rule, it has to be one on which, when you apply indifference reasoning, when you say I assign credence 1 over n to all possible branches, had better be indexed to some particular time. You don't just apply indifference willy-nilly. You choose a particular time at which you're going to be indifferent. So Simon Saunders proposes and then rejects for independent reasons that I'll get to, a rule that says essentially, if upon some branching event n branches are created, m of which realize an eigenstate alpha, then your credence that you're on an alpha branch should be m over n. This is a diachronically consistent branch counting rule because it says specifically, no, only apply indifferent credences at T2, don't apply indifferent credences between all 3 branches at T4. So what you get are respective credences of 1/3, 1/3, 1/4, 1/4, and 1/2 in the propositions that the results were up, 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 down, or just down for the first particle. I think that this proposal is on the right track, at least for somebody who wants to defend branch counting in some capacity. But I think its success is that it highlights that we have to pick some time index for our indifference measure over branches. But I don't think it necessarily has to be the time of branching. So consider the following pair of cases. So I won't read all of this horrendous text, but I'll just give you the basic idea. In the case that I'm calling double observation, you imagine that you perform these 2 spin measurements, and you observe the result of each spin measurement immediately after you've performed them, kind of just as the case that I gave would suggest. And in the second case, what I'm calling delayed observation, you keep your eyes closed throughout the whole process. Some spin measurements are made. The universe branches first into these up and down copies, and then to these 3 different copies. And you keep your eyes closed throughout the whole process. You remain uncertain about what the results are, and then at T4, you open your eyes and you assign some credences to the proposition that the initial particle was spin up or spin down. And so local branch counting, of course, would have it that you should adopt the same credences in either of these cases, because the time index is always at T2, and then you just conditionalize back on your indifferent credences at T2 to assign credences at T4. But I am suggesting an alternative branch counting rule. Again, this is kind of just a tweak, but I think it's one that I think is potentially an improvement, which I'm calling indexed branch counting, which essentially just says, yes, pick some time at which you're going to be indifferent between the results of between being located on this branch or that branch. But that time at which you index your indifference measure should not be the time of branching, but the time of observation. So in double observation and delayed observation, this rule gives different results. It says that here if you observe the result at T2, you should assign credences 1/2 and 1/2, and then go on and update in the usual way. But if you don't observe until T4, you should assign credences of 1/3, 1/3, and 1/3 to being on any one of these 3 branches. Okay, I'm not yet defending that. I'm gonna go on to offering some more global defenses of branch counting, and specifically indexed branch counting, in which I will give some attention to why I've shifted the time index relative to the local branch counting rule. So the first kind of general justification I'm going to try to give of indexed branch counting as a rational way to set, or at least a rationally permissible way to set one's credences in these branching scenarios, has to do with the concept of accuracy. So standardly in formal epistemology, the inaccuracy of some credence function is defined by its Breyer-Loss function. So when you have W being some classically consistent assignment of truth values to all of the propositions in some algebra of propositions, you understand the inaccuracy of a credence function in that outcome as being just the sum of the squared distances over all the propositions in the algebra of the credence function's assignment and the truth function. Let's say if it's true, it's 1, your credence is 0.7, then the contribution for that proposition will be 0.3 squared. In Everettian theory, if we want to sort of generalize this idea of inaccuracy, we need both a diachronically consistent, i.e. time-indexed measure of inaccuracy, just as before, And we also need a way that we can sum inaccuracy across these different branches. So it's not just one successor that has some inaccuracy function. It's all of my successors. And if I want to decide how I'm going to determine my preferences among all these branching futures, or how I'm going to set my credences in these outcomes, if I'm interested in accuracy or in some stand-in for accuracy, like for utility or whatever you like, I'm going to need a way to sum that across branches. So as to the first of these issues, I'm going to define the quantum Breyer loss function for some credence function CR on a branch B, just as before, but with this time index. So it's just the sum of the squared distances between the truth function on that branch and your credence function, all indexed to the time at which you observe the outcome of that event. So now the question is, why index the accuracy measures the observation time? I think we can offer a few kind of at least prima facie motivations for this. One is that I think that when I observe the result of some experiment, this is the time in which I'm in a position to confirm or disconfirm the scientific theory. So imagine that I had two theories, one which said whatever physical magnitude determines the probabilities. It fluctuates wildly in some very weird ways right until you observe the outcome of an experiment. But once you observe, the probabilities are very normal and they are whatever we want them to be, whatever that comes to. And then you had a theory which said, yeah, the probabilities are exactly as we want them to be, except when we perform measurements. Both of those theories seem weird. They might be distasteful for all sorts of reasons, but I don't think the former theory runs into problems with empirical confirmation. It's like the frequencies that we observe in the lab, the results of probabilistic processes that we actually observe are basically exactly as what the theory tells us we should expect. So at least in that case, in terms of where do we care that our credences be accurate, I think the time of observation is the right choice. This is sort of like an accuracy-theoretic analog to like the times at which you receive and exhaust payoffs in standard decision theory. So it's like, I should really care about maximizing utility at exactly just that time in which I'm going to receive some payoffs, whether it's, satisfaction that my credences are vindicated or cookies or whatever. So that's kind of the basic motivation. But I also think that this is kind of a rather small point compared with the second question, which is how should we measure accuracy across branches? I think one can kind of immediately see that if one wants to get the Born rule out of Everettian quantum theory, one will want to, in some way, weigh each branch by its quantum amplitude, as opposed to measuring inaccuracy in a way that is simply additive across branches. Clearly this weighing each branch by its quantum amplitude is going to be a lot friendlier to Everettian approaches to probability. The first will not. I hate to be unfriendly to anybody, but I am going to try to defend the first of these options. So let's define, just for now, this is a definition, but let's define the total successor inaccuracy for an agent A as a simply additive function across branches. You just take this inaccuracy measure on a branch at a time that I've given here, and you sum it without any weights for the quantum amplitudes across all branches. And I'm advocating a principle of rationality, which says that in setting one's credences in the outcomes of quantum mechanical experiments, agents should take care to minimize this total successor inaccuracy function. So, okay, how could I possibly justify this? I think there are all sorts of complaints you might make. One such complaint might be that it conflicts with all sorts of other plausible constraints on rationality that do deliver the Born rule and that enter into approaches to Everettian probability that have been advocated by people like Sean Carroll and Chip Evans and by Lev Weidman and Deutsch and Wallace and so forth. Another possible complaint might be that this just simply begs the question against the Everettians, and this is something that I'm going to address towards the end of this section, and probably lots of others, which I would love to hear in the Q&A. So taking a step back, when one tries to justify the Born rule in an Everettian context, oftentimes what we're doing is we're starting with some kind of axiomatic principles of decision-theoretic or epistemic rationality. So, for example, you have in Deutsch and Wallace and some of the early approaches to this. There's measurement neutrality, which is the idea that given an observable, a state, and a payoff function, a rational agent had better be indifferent between any two betting scenarios that agree on the state, the observable, and the payoff function, but disagree on any additional physical details about how the measurement is performed. So basically, any of these details about how you set up the measuring apparatus or anything like that shouldn't matter for what rational credences you assign. Another such principle is what David Wallace more recently has called branching indifference, which essentially just says you rationally shouldn't care about branching per se if some operation leaves you in a whole bunch of different macro states, in a whole bunch of different branches, but it doesn't do anything to change your payoff function. You shouldn't care whether I hit the button that just makes you multiply 1,000,000 times or something. Each of these principles are like strictly additions to classical decision theory. Each has some independent motivation behind it, but also each has been independently criticized in this in the paper, which you can find on BJPS or on Phil papers. I've given some citations of who has criticized these and why. But my interest here is not really to criticize any of these particular approaches, but rather to just say, well, I could propose also some sort of axiomatic principles of rationality that also seem fairly reasonable, and which leads us to derive rules other than the Born rule. And I think that these are arguably as well motivated, if not more, as the assumptions that figure in the Everettian approaches, though I'm sure many will disagree, and I'm happy to hear your disagreements. So taking another step back, when we are using these kinds of decision-theoretic approaches to justifying the Born rule, what often happens is we first postulate, as happens in standard decision theory, that agents are rationally required to maximize expected utility. And then expected utility is calculated both via a payoff function, but also via a prior credence function in the likelihood that this or that outcome in which I receive this or that amount of utility will occur. And oftentimes these Everettian approaches to probability, and I'm not saying always, but often what happens is you start with these kinds of a priori constraints on the rational credences that we use to calculate expected utility. But another approach could be to just say, look, again, with some caveats, exactly what the future branching structure looks like. And if that's true, then you can just maximize utility. If you have some way of summing utility across branches, again, not yet taking a position on which one to use, but if I hand you a cross-branch measure of accuracy or utility or something of the sort, what some have called a caring measure over your successors, I can choose a strategy that will guarantee that utility or accuracy or whatever else will be maximized. And it seems kind of reasonable, generally speaking, that if you can just maximize utility, you should do so. Some Everettians have taken that kind of approach. So I think Hilary Greaves has and David Papineau has, where they just say, we know exactly what the future branching structure will look like. Let's pick a measure over branches, something like a caring measure, and just maximize utility or whatever we're interested in maximizing on that particular measure of accuracy across branches. And I think that's I myself think that's a very reasonable starting point. I will say that I think this is kind of where the incoherence and quantitative problems mingle. So if your metaphysics of branching persons is something like, all of the observers, even kind of pre-branching or pre-decoherence, are numerically distinct, and they're all just individually trying to figure out which branch they will end up on in the future, I don't think this argument will really appeal to you. But I think that if you think of my relationship to my future successors as being sort of the very similar to, in the one world case, my relationship to my future self, then I think this just like at least intuitively seems like a more reasonable argument. But if one buys that you should just maximize utility on some preferred measure, the big question becomes, how should we weight utility across branches? Should we do it by a simply additive function? And why should we, as I'm advocating? So I think like at least some prima facie argument would be something like this. All of the different branches of the wave function, high or low amplitude, are at least approximately kind of structurally isomorphic. And it seems naturally that if that's true, we should weigh them equally in our quest to maximize utility or accuracy or whatever. So what we often think of as being, very like value-making states of affairs, whether it be pleasure or pain or satisfactions that my credences have been vindicated, or the taste of cookies or something, these all seem to be equally present on all branches, given that the functional and structural properties on each branch don't seem to depend on their amplitudes. So in decision theory, we at least want to allow agents to maximize more or less whatever they want. So here I'm using accuracy, right? Partly to just make the formal argument more convenient, but it's kind of a convenient stand-in for any kind of utility. Like I said, pleasure, pain, whatever you like. But if an agent says, all I want to maximize is pleasure, and pleasure I understand to have something to do with, the way that it feels to be in such and such experience on such and such a branch, this does seem to be at odds with the requirement, not that they maximize pleasure, but that they maximize amplitude-weighted pleasure, or really anything other, I think, than a non-weighted sum of pleasure across branches. So one response that you might make, and I want to be clear in fairness that I don't think this is actually something that Lev Weidman is saying. It's kind of the closest that I've seen Everettians come, or at least hint at this kind of strategy, is to say that actually, yeah, all of these things that we care about, pleasure, pain, whatever else, they actually do count as valuable. They actually are instantiated to a greater degree, in some sense, for high amplitude observers versus low amplitude observers. So the reason that I say Weidman might kind of at least initially appear to be advocating something like this, and please, Lev, if I'm misrepresenting you, I'd be eager to hear, that the branch amplitudes determine what he calls the degrees of existence of these relevant branches. So maybe one might infer the pain of my low amplitude successors matters a whole lot less than that of my high amplitude successors, because the former sort of exist less than the latter. But I think that, as Weidman says in the relevant paper, I'm quoting now, all physical parameters such as mass, spin, magnetic moment, etc., are independent of the measure of existence. A neutron with a tiny measure of existence moves or feels exactly as one with measure one, or with very high measure. So as important as measures of existence may be, so for example, with like determining to what degree can your branch be interfered with by an experimenter or something like that, I think there are lots of things that agents really do care about, like how things feel, what they might be interested to maximize in decision theory, that don't seem to depend on this measure of existence. So I think unless an argument can be given that actually there is some sense in which maximizing pleasure just means maximizing amplitude-weighted pleasure or something like that, I think this strategy probably won't work. So the second strategy, and this is actually closer to what I think some Everettians have said, is that yeah, we should have a kind of caring measure over our successors, and just as a matter of stipulation, we should use this amplitude, or I guess square amplitude measure of accuracy, of utility, or of whatever else. But I think this would be a very extreme proposal, because it's going to require, for example, as I said before, that if you're interested in maximizing pleasure, minimizing pain, in a way that doesn't depend on amplitude, just say supervening on their phenomenal properties. You're just not allowed to do that. So you should, for example, take about some action that will bring out, enormous pain for millions of your low amplitude successors in order to bring about some like fairly small degree of pleasure for your high amplitude successors, despite again there being no qualitative difference, as we've assumed if we're taking this strategy, between high and low amplitude pain and pleasure and so forth. So I think this is an option. I don't have a knockdown argument against it, but I think it's one that I find fairly hard to swallow. So another issue here might be, well, aren't I just begging an extremely central question against defenders of the Everett interpretation? Some people here might feel that way, and I apologize. But so this kind of thought would go, it seems like a very central commitment of the Everettian theory that branch amplitude really is in some way intimately connected to notions like utility and probability. I mean, it's just almost like a fundamental commitment of the theory that branch amplitude really matters. But I don't see, and I'm open to being corrected on this, but I don't see why these should be commitments of the theory. Seems to me that the theory is simply saying the universe obeys the wave function. And the universe is fully described. The wave function obeys the Schrodinger equation, and the universe is nothing but the wave function. And so notions like branch and probability at the fundamental level don't enter into the theory. If we are to derive some probability rule or some idea about how you should weight the utility or accuracy of your successors, that's going to have to be derived from, yes, the fundamental theory, but also in conjunction with auxiliary assumptions about, for example, rationality that have nothing directly to do with the theory itself. And so when I say I'm denying those assumptions or postulating principles that conflict with those assumptions, I'm not saying anything, I think, that conflicts with the core commitments of Everettian theory. So I'm not going to really go over this derivation, partly because I think it's fairly trivial. In fact, it almost just parallels the argument that the Breyer loss function is strictly proper. But essentially, what I'm saying here, and you can pursue the details in the paper if you like, is just to say that if you adopt maximize accuracy for successors, if you say I should minimize total successor inaccuracy, again, wouldn't take too much effort to replace accuracy with utility or something like that. And I'm measuring inaccuracy in a simply additive way across branches, then I'm going to have to obey index branch counting. Again, this is where the accuracy measure is indexed to times. Again, to show that this measure is in fact minimized by index branch counting is fairly straightforward. So I apologize for the very ugly slide, much like many other ugly slides in this presentation. But I'll kind of skip over this. So if you're unconvinced by the accuracy argument that I've given, and how could you be? But I'm sure many will be unconvinced. I'm going to offer another alternative argument, but I'll go over this one also quite quickly because it's a fairly straightforward argument. So there's a very popular idea in formal epistemology, in statistics, in decision theory, called exchangeability. Probability functions are exchangeable kind of roughly just in case they are indifferent between any two sequences of events that disagree on the order with which events occur, but agree on the frequencies or agree on the sum of the pardon me, of the values for some random variable divided by the total number of trials. And oftentimes it's been taken to be, say, for example, by De Finetti, an assumption of some derivations of some important results in formal epistemology that rational credence functions be exchangeable. But again, exchangeability is a feature of some probability functions and not others. But if you say that under certain circumstances, it just kind of seems plausible that seems fairly natural that order shouldn't matter when you already know what the frequencies are going to be. So so in this case, I'm suggesting that the analog is you've got a branching structure and you've got a frequency of observers across these branches who see this or see that, as long as the frequency is held fixed, but the identities of the observers across different permutations, the identities of the observers are permuted in some way, you should be indifferent between any two such outcomes. So quantum exchangeability, as I'm calling it, says that for any two outcomes that agree on the frequencies of observers who end up on an alpha branch, or I should say, who see alpha at the time of observation, the agent should assign equal credences to any of those two outcomes. Okay, and it's again fairly easy to see. I won't bore you with the fairly rudimentary details that if you take some proposition that I am on this branch, that leaves a number of other permutations of the identities of my successors across my counterparts across other branches, and they're all going to leave equally many possible permutations. So you have to assign by quantum exchangeability a credence of 1 over n to each of these propositions. So, and then if some eigenstate is realized on m of those branches, you have to assign m over n, and that is just index branch counting again. Now, I just want to take stock. I think the first thing that I should say, to be intellectually honest, is that these are absolutely assumptions one has to make about rationality that are absolutely additions to normal decision theory. They're things that one might find intuitively implausible, others might find intuitively plausible. But I think that's, to a certain degree, kind of the name of the game when we're trying to justify the Born rule or any other probability rule in Everettian theory. I think we have to make some assumptions about rationality. And part of my purpose in this paper has been to say, well, look, these kind of seem to me like as good as any rationality principles. So doesn't it at least put some pressure on the idea that the Born rule would be the only rational way to set credences in branching scenarios? Given that we can derive an alternative rule from some other potentially plausible principles of rationality. And I just want to say kind of a very global point in favor of the kinds of principles that I assume, is that I think that they stem from an exceedingly plausible idea that the knowledge of frequencies, be it future frequencies or something of the sort, very, very strongly constrain our credences. And I think they often override other considerations about rationality that would plausibly apply when we are ignorant of the frequencies. So, for example, suppose that I tell you that I'm going to show you a video of 10 consecutive dice rolls, and I ask your credence that the outcome of just the first trial will be 3. So 1/6 seems like a very reasonable answer, whether it's to do with symmetries in the die, some kind of indifference reasoning, or something of the sort. But what if I tell you ahead of time that half of the die rolls resulted in a 3? Then it seems pretty reasonable that your new credence should be 1/2, and that, yes, these symmetry-based considerations or whatever else you use to arrive at 1/6, they were very reasonable, but I think they're really overridden when I've told you exactly what the frequencies are going to be. And I think something similar is going on with my justifications, or my attempted justifications, of index branch counting. I think that your knowledge of the quantum state and the future branching structure, again, up to precision, which I'm going to address in the next section, allows you to obey some very natural, I think, seemingly perfectly rational strategies for setting credences in branching scenarios. In particular, they allow you to simply maximize accuracy on some measure. I would like it to be the simply additive measure, or they allow you to adopt an exchangeable credence function in which, kind of arbitrary permutations of the identities of observers don't make any difference to your credence function. And these, of course, conflict with the Born rule, though again, modulo what I'll be talking about in the last section. one might now say, okay, this is well and good, seems very reasonable. I suspect some people still will not say this, but one might say, okay, it seems like IBC would be a rational way to set your credence if it were even remotely possible for you to do that in a branching scenario. But this is just impossible because there's no such thing as the number of branches. This has been very strongly stated by David Wallace. Hilary Greaves as well has a section of a paper, I think from 2004, in which the title of the section is "Egalitarianism," the idea that you should care about your successors equally, is just incoherent. Plausible maybe, but incoherent. So this is, I think, the most popular argument against branch counting, both from looking at the literature and from talking to people. So to address the objection, I'll need to say a little bit about decoherence. So here's a fairly simple example from David Wallace about how decoherence works. So imagine you have a state that begins some state for a particle, a state in position space, which is a superposition of being kind of very well localized in position space around Q1 and being well localized in position space around Q2. And then you imagine inducing a scattering interaction on some second particle in the initial state phi sub 0, which would yield post-scattering states of phi 1 plus and phi 2 plus respectively, due to interactions with the first and second wave packets of the first particle. So the dynamics for any one wave packet with that initial state would lead to a product of the initial state of the second particle with the initial state of the well localized first particle, leading to a product of the same initial state for the first particle and a particular corresponding post-scattering state for the second particle. And unitary evolution of the system gives a superposition of different product states of the first particle was located roughly here, and then this scattering interaction occurred, plus the first particle was located around here, and this scattering interaction occurs. And so now the systems are entangled. So when you look at the density operator for the first particle system, it evolves like this, where you have these on-diagonal terms for the density matrix, which are just the square amplitudes, which we would like to be the probabilities, but they also have these off-diagonal they have these off-diagonal interference terms, which notably depend on the inner product of each depends on the inner product of these two possible post-scattering states. When the systems are highly entangled, these two inner products are very small, so the off-diagonal terms very, very nearly vanish. And what that kind of comes to physically is these two kind of bumps in the wave function almost don't interfere with each other at all. They kind of go off their separate ways. And this is kind of why we often talk about what happens with decoherence as inducing a kind of branching structure. We can kind of describe these more or less decoherent bumps as separate worlds because they represent these very stable, very useful patterns in the wave function. I should also say decoherence is not the only way that Everettians understand branching, but this is one fairly popular way. And so when we supplement decoherence theory with some kind of, I think fairly natural criterion for how we think about the way that we get emergent ontology out of our fundamental ontology, we get this many worlds, branching picture. And what Wallace employs is Dennett's criterion, which is to say that any macro object is a pattern. The existence of that pattern as a real thing depends on the usefulness of theories that admit that pattern in their ontology. And one can kind of see why it would be very useful to talk about these different almost non-interacting bumps in the wave function as being kind of separate worlds or separate branches, or these additional kind of emergent entities that flow in this natural way from how the fundamental dynamics work. So consequently, branches are sort of understood as these emergent features of reality, endowed with only an approximate structure by decoherence. So essentially the question is, how much interference is too much interference? The Schmidt basis, where there's zero interference, is generally thought not to work. So the interference has to be sufficiently small, and sufficiently small is essentially just considered to be a vague term. It's not something that the theory needs to specify because it's an emergent feature of reality, just as, tables and chairs can be vague, branches can be vague. But then there is no precise number of branches at all, so there's really nothing left for us to count. And so what could a branch counting rule, how could that even make sense? It starts to look sort of incoherent. We're counting these things, numbers of branches that don't even exist, are not well defined in the theory. But I want to resist this line of argument. I want to at least propose some options for how we might think about vagueness in connection with a branch counting rule. So I think many of you are familiar with the principle, which essentially very roughly tells you that you should, if you think that the chance of some proposition phi is x, then your credence in phi should be x. But suppose that the objective chances are themselves vague. So for example, if you think that the chances come from the past hypothesis, the statement that the law potentially that the universe began in a state of very low entropy in conjunction with this uniform on some natural measure, usually the Louisville measure, over the probability measure over the possible microstates that the universe could have began in, you will get chance laws that could well be vague. I would point everybody to a lovely paper from Eddie Chen, recent paper called Fundamental Gnomic Vagueness for more details here. But these chance laws might be vague over possible precipitations of low entropy, or over ways of partitioning phase space into macro states, and so forth. But I think it would be ill-motivated to simply reject the principle because it instructs agents to conditionalize on something vague. I think it's very crucial for our ordinary use of chance reasoning that we not rule this out of hand. And in fact, it's for this reason that a lot of ink has been spilled in how to try to understand how we can obey something like the principle in light of the possibility of imprecise chances. So for example, Yoav Isaacs, Al Hayek, and John Hawthorne have proposed this imprecise principle, which says that if the chances are vague over some interval, then your credences should be vague over that interval. I would also like to leave some room for the idea that the endpoints themselves be vague, but for now, let's not worry about that. And I think we can essentially formulate a very analogous branch counting rule when the numbers of branches are imprecise. So if the ratio of alpha branches to total branches is vague on some interval, let your credences be vague on that interval. Imprecise credence is a very live option for how to understand chance credence norms in light of imprecise chances. So sort of, why can't we at least consider doing that here? Another option is that you could adopt what's called a supervaluationist logic, which is a way of understanding the truth value of propositions in vague contexts. So we might have some set of admissible precipitations of something, for example, branches, and supervaluationism tells us that some proposition is true if it's true on every admissible preciptation. It's false if that proposition is false on every preciptation, and it's neither true or false if it's true on some and false on others. So the normative facts, the fact that you ought to adopt this credence function, might be vague. It might not be determinately true or false that you ought to adopt this credence function. But there are some biconditionals that are not that are actually true or super true on this approach. So for example, if I said some credence function is quantum exchangeable if and only if it obeys index branch counting, well, give me any possible admissible preciptation of branch, and that's going to be true for the arguments I just gave. Same thing about the sort of normative link between maximize accuracy for successors and the requirement that you obey index branch counting. both are true on all precisifications of branch, even though it's not true of any one credence function that you are non-vaguely required to adopt that credence function. This is a fairly ordinary thing in the metaphysical, logical, philosophy of language research on vagueness. Lots of options I've left out, but these are at least two. And so the question is, we've got these possible ways, seemingly fairly natural ways, that we might extend index branch counting to vague contexts. So why is it a problem here, if not also in analogous cases of vagueness? Again, very open to hearing either why this case might be different or why those general approaches to vagueness are no good. But that's my basic response to the vagueness worry. So I will try to be as quick as possible and address Simon Saunders's recent work on branch counting. So essentially, what Saunders is doing is saying we've got this decoherent history space. We have to coarse grain it in some way, and we should coarse grain into cells of equal amplitude. And so the consequence of that is that the ratio of branches realizing some eigenstate alpha j to those realizing some eigenstate alpha k is equal to the ratio in the squares of their wave function amplitude. Then, of course, we just have a kind of branch counting rule for how rational agents should set their credences, which essentially just says, match your credences to ratios in branch count, which in this case means obey the Born rule. I think that this is exactly the kind of proposal, given everything I've said up to now, I would sort of like to have. I would like to be able to say that, yes, branch numbers do covary with the amplitudes, and to say that we have some well-motivated reason to say that they do. And so I think, I think that would be great. I think this is the kind of proposal that would satisfy me if it pans out. And so I think it's totally on the right track. I do have one concern, and then I will get to Saunders's main motivation for why we should adopt this rule after I state my sort of preliminary worry. So my main worry is that I kind of think that we get a branching structure from decoherence theory, plus some suitable conditions on how we get macro ontology out of fundamental ontology anyway. So, for example, this is an example from Saunders. Suppose that you have some apparatus that registers spin states of a particle. There are, n up number of decohering states of the approximately decohering states of the detector recording spin up. In fact, there will be zillions of them. I mean, kind of imagine like, all right, anywhere around here would be spin up. The detector could be pointing here, or it could be pointing there, or it could be pointing there. There are going to be lots and lots and lots of different environment states that are approximately orthogonal, all of which still can correspond to the particle being spin up. So really, there are zillions of these branches. And there are similarly n down states of the detector recording spin down that are more or less orthogonal. And let's just assume that there's a precise interference threshold modulo what I said in the last section for convenience. So unitary evolution will now give the idea that after a measurement is performed, there are going to be these zillions of decohering branches on which you have particles spin up, and detector is in the first spin up state, all the way up to the n up spin up state, similarly for spin down. But as Saunders notes in his papers on branch counting, these numbers depend on how many approximately orthogonal ways the device can register the spin states, but not on the amplitudes. Oh, or at least they don't vary perfectly with the amplitudes. I mean, so if you go back to here, right, the interference terms, which are telling you how many branches are sufficiently non-interfering, they don't covary, at least not perfectly, with the square amplitudes. And so my sort of feeling is that there is, let me rewind for a second. So of course, this approach, as Saunders recognizes, is inconsistent with thinking of the ratios as coming from this ratio of n up to n down. There is no particular interference threshold which via decoherence theory would give us the results of equiamplitude branch counting. And this is why instead we have to postulate a branch counting rule where instead we just coarse grain into cells of equal amplitude. But my feeling is that this idea, the idea that we should actually understand the ratios as just n up over n down, is something very close to what we get when we take decoherence theory and add to them some fairly natural principles of macroontology, such as, some expansion of the quantum state adequately describes branching whenever the interference between the components is sufficiently low, or macroscopic objects are sufficiently well localized in each wave function component. In each of these cases, it seems that we get an approximately defined branching structure that has little to nothing to do with the square amplitudes. And so if our principles of getting macroontology out of fundamental ontology are essentially, there are these branches whenever interference is sufficiently low, trying to pick some, although vague, range, pick some vague range of admissible but consistent interference thresholds. We get that sort of original old branch counting rule rather than the equiamplitude branch counting rule. And I sort of was of the impression that the main point of branching was supposed to be that it followed from some, reasonably well-motivated principles of macro ontology. Again, not to leave out the possibility that some principles could be found, but this is where I will now get to Saunders's motivation for why we should count branches in the equiamplitude way. So Saunders appeals to the idea of continuity of the branch numbers as a function of the quantum state. So if you perform some spin measurement on some state, cosine omega k up plus I sine omega k down, where theta k, where theta k is equal to pi over 2k plus 1. Clearly, this state converges smoothly to the up vector in the Hilbert space norm as k approaches infinity. It's this, the first component goes to 1, the second goes to 0, and they do so smoothly. But the ratios in branch count, where we're just counting up the different ways, approximately orthogonal ways the spin system can measure up or down, remains constant, or at least doesn't covary perfectly with the square amplitudes. And it does not converge in particular to R infinity equals 0. But of course, we want to say that R infinity equals 0 because we want to say that if the amplitude of some branch is exactly 0, there'd better be no people or tables or anything there. There should be no branch there at all. And so the consequence is that we're going to need to have a branch counting rule which is discontinuous with the state. And Saunders says that this is a very serious problem for the original branch counting rule. And this would then be very strong motivation in favor of the equiamplitude branch counting rule, where the ratios do smoothly vary with the state. Because as he says, continuity in the amplitudes in the Hilbert space norm, the norm topology, is essential to decoherence theory and the unitary dynamics, as likewise to spectral theory and the whole edifice of quantum mechanics. But as far as I myself can tell, I don't really see how any of the above-mentioned features of quantum theory depend on the branch numbers smoothly varying with the state. And it's hard for me to see how this could be, because the branch numbers are part of the emergent ontology. They don't, for example, when we say the unitary dynamics, they don't have anything to do with the unitary dynamics because they're these macro features of the ontology. So they don't impact, as far as I can tell, anything to do with the fundamental theory. So like I said, continuity in the wave function in the norm topology is something we need very desperately for the dynamics to work, because the dynamics are given by a differential equation. So we need continuity in the amplitudes. But I don't see why the dynamics should depend on what rule we use to count up these branches or to calculate the probabilities. So then the question is, like, what principle is at work here? Is it that any physically respectable function on Hilbert space should continuously vary with the amplitudes? I think, of course, we can dream up all sorts of functions that don't, like, is an energy eigenstate, this example is due to Dave Baker, clearly defines a discontinuous function on Hilbert space. So my main worry, and again, preliminary, I'm sure that maybe some reasons could be given, and I'd be very eager to hear what they might be. But I feel that we need some deeper motivation for why we should abandon a branch counting rule, which does define a discontinuous function on Hilbert space. That is something that, to me, seems to follow fairly naturally from decoherence theory. So what is the broader motivation for why a discontinuous function on Hilbert space would be such a big problem? In other words, but again, that's an open question, and I'd love to hear more about that. Certainly, if those questions can be answered, I think that this remains a super promising approach. So given that I've run a few minutes over time, I won't give too much of a conclusion, but I'll just say, in brief recap, Everettians can postulate some seemingly fairly natural sort of rationality axioms that tell you to obey the Born rule. But I think that an alternative strategy for setting credences can be derived from what I've argued are potentially even more natural assumptions about rationality. And then the second thing is that I've tried to give some argument for is that often Everettian arguments against branch counting either don't apply here, like with the diachronic inconsistency worries, or stand in need of some stronger motivation, such as vagueness or continuity and things like that. So, and unless some independent arguments can be given against these rationality axioms, or the separate worries about the viability of branch counting can be strengthened, I think that the probability problem for Everettian quantum mechanics will potentially be deepened. So thanks again, everybody. I especially appreciate that those who disagree have bared with me through what I'm sure was a very painful experience. But again, thanks for being here, and I really look forward to hearing what you have to say. And also thanks to Jacob for this really cool AI picture of my paper.
All right, we're back for the discussion Q&A. Sean, please go ahead.
Thanks, Jacob number 1. Thanks, Jacob number 2. That was a great talk. I really enjoyed it. You did not change my mind.
Really?
Apologies to Jacob number 2, and also to Simon that I do have to go, so I have to get this out quickly. So don't feel bad if I run away after the question. But I do think you're begging the question against Everettians. I think you kind of know that you are, which is why you kept trying to preempt this worry in the following sense, that if you just stick by the idea that everything should be weighted by the amplitude squared, including your accuracy measure, etc., then everything's fine. Then the Born rule works, and you're doing everything right. So the whole argument, it's not really begging the question, it's a little unfair, but the whole argument hinges on, rather than just directly talking about how to assign probabilities, shifting it to how to measure accuracies, and then treating different branches as equal in that formula, which maybe is begging the question. But I completely agree that there's nowhere in the postulates or stipulations of Everettian quantum theory that you should care about every branch by the amplitude squared, right? It is just the wave function evolving over time according to the Schrodinger equation. But then, for that matter, the existence of things called branches is not part of the postulation of Everettian quantum theory either. Those are human conveniences. Those are higher level emergent things. And I don't think that the vagueness argument works at the end of the day, because I don't think vagueness is the point. I think that the point is that there are more than one way to define branches. Some people will say that if an observation happens very far away, the branching happens instantaneously. Some people will say that it's inside a light cone. Some people will say if you decohere with just, becoming entangled with a single qubit, that's a branching. Others need Avogadro's number or something. And there is one way of assigning caring or measure to different branches that is completely agnostic to all that, which is just using the wave function squared. So even though the theory doesn't insist or stipulate that you do that, it is strongly suggesting, I may anthropomorphize the theory, it's strongly, guiding you in the direction of doing that. And just the final thought then, so why work so hard, basically, is the point. I think what I'm going to do is ultimately agree with Lev's philosophy that whatever it is indicating to you, that since you're making up branches as human constructions, the way to treat them and care about them is as the wave function squared in every possible way. I just think that the formulation of the degree of existence might be a little bit rhetorically misleading. Sure, properties of neutrons and so forth are not affected by the amplitude squared, but all of those properties are measured by other people on the same branch. They're all relative properties of people within the branch. So we know why they're not affected by the amplitude squared. It's things that matter across very many branches at once that depend on the amplitude squared, and the probability is absolutely one of them. So my mind is open, but not yet changed. But anyways, great talk. Thanks.
Thanks so much, Sean, and thanks again for being here. Yeah, I think that maybe in retrospect it would have been better to just say, well, here are all these ways that people have tried to justify the Born rule, and here are these ways that are kind of off the table, or here are these things that are here are these consequences. At least consequences that people might find some people might find unwelcome. Like, for example, you just have to weight the things by psi squared, and you maybe don't have to, but at least as far as any proposal on the table that I know of, you have to do it sort of as a matter of stipulation. And it stands, I guess maybe a softer way that I could have put it is, it stands in tension with this idea that we find in decision theory, that if you want to maximize pleasure for your successors, you should just be allowed to do that, and you shouldn't have to care about the amplitudes. Not to say that that's a knockdown argument against it, but just to maybe that's something some people might find as an unwelcome consequence or something.
Yeah, I mean, almost to agree with you, but at least to find the point of agreement. Everett is demanding something very different of other ways of maximizing utility. Like, usually we can just count people. Everett says we have to weight people. And I think that once you take that leap, then you're happy and self-actualized and you can sleep at night. And, I'm sorry that not everyone is ready yet.
Yeah, I would definitely like to hear more, but I don't want to keep you from where you have to go. But definitely, I would like to hear more about exactly where we differ on the question of to what degree is the theory sort of very heavily suggesting this. Like, as you mentioned, it's not a consequence of the theory. But maybe that's a story for another time.
Cool. I have to go get some shots. So thanks very much.
Okay, enjoy the shots. Thanks again, Sean.
Good to see you, Sean. All right, the next hand is Simon. Simon, please go ahead.
Yeah. Okay. So Jacob, thank you. And both Jacobs, great talk. Actually, I thoroughly enjoyed it. I do disagree with several strands in it, as not surprisingly, I think. But let me just make 2 points, because they're both perhaps the most important anyway. So one of them concerns this business of continuity. And I would put it to you that any state detection apparatus, any state measurement apparatus, is constructed and modeled in physics in ways that depend critically on continuity in the norm topology in Hilbert space. So, and the dynamics, of course, depends critically on continuity in the norm topology. And if one is committed to dynamical approaches as relevant to most things that matter in reality, then it seems to me there's a prima facie case that indeed you better care about continuity in the relevant topology when working with a physical theory. And I'm aware that you somehow sort of get out of that and just seem to sort of negate it. And I find it a little bit curious. I mean, one way I would put it, though, is this. We've got it's one person's modus ponens is another person's modus tollens. So is one going to be charitable or not charitable? So let's put it this way. So if there is another branch accounting rule which is continuous in the norm topology as opposed to one that is not, then that would seem to me prima facie reason to favor that branch accounting rule. Okay, so that's a quick comment on that. But the other point I would like to make is that I think you're underestimating what goes on in a decoherent history space, because typically what you've got is a parameter space, and that typically will not be a discrete space. It'll involve continuous degrees of freedom. Sure, there's a level at which you fine-grain too much and then decoherence is an issue. But look at the vast range of coarse grainings that you've got where decoherence is guaranteed. So if you're going to look at a frequentist account of probability, and you're going to define the frequentism in terms of an ensemble, and it's a finite ensemble, there's a vast number of different ensembles of branches that you can define, all of them decohering, but perhaps giving you different relative frequencies. So this becomes the core question. Do you have consistency referring probabilities for some macrostate if you're going to appeal to different ensembles, all of them equally good in accordance with some set of rules? So you sort of need rules. You can't just say, just count branches simpliciter. There's no such thing as branches simpliciter is the issue. So the criticism that I would make, apart from the continuity criticism of the branch counting rule that you are advocating, is that you don't get consistency defining relative frequencies with respect to different ensembles. In fact, you've got a sort of a complete failure of any consistency, whereas for the equi-amplitude rules, you do guaranteed consistency. So that's not there in print. It's not in my 21 paper, which is the transactions of the Royal Society, isn't it? But there's another paper I'll be putting on the archive very shortly, and I would very much welcome discussion about it. But I think these are the main two concerns I have with the structure of your argument.
Okay, great. Yeah, I mean, I have nothing knocked down to say against any of them. Those are very helpful correctives. So I take it that the second worry has to do with the idea that we're looking at two different ensembles of systems. Is the idea that you're not going to have a consistent way of defining frequencies across them just because of the way that the branching structure is so sensitive to the details of how the experiments are set up, or am I missing something else?
Well, I think you actually have to look at the concrete argument. It's not very long, but it's probably too long for me to put it into words such that people could understand it. So, but the worry is that, I mean, here's one rule for picking an ensemble, which is Boltzmann's. Choose a fine graining of phase space or the relevant parameter space so that you've got equal volumes. This would be using Lebesgue measure or Liouville measure for Boltzmann, but we could do it with some other measure. So that's a rule. And then the further requirement is that the branches have got non-zero amplitude with respect to those equal volumes. Fine. Now you apply that rule with different choices of how big is the volume and different shapes for the volumes, even though you've chosen, what is the size of the volume, you get different ensembles. Now, do relative frequencies referred to those different ensembles, do they agree with one another? And the answer is they don't.
Right. Okay, good. So yeah, I'll be very interested to read that and to discuss more with you. And then I think just as to the first question, I think that what would be a major weak point in the argument that I gave concerning continuity, and this is probably something that I just personally need to understand better, is to what degree is the there's for example, I picked out maybe unfairly sort of the easiest example, which is just the fundamental dynamics. But to what degree does decoherence theory, in what way does decoherence theory depend on continuity, the amplitudes? Is that equivalent, or does that at least bear on questions about whether it depends on things like continuity in these emergent branch numbers? Does it depend on things like continuity in the probability rules, or is it more of a kind of just naturalness considerations? Like it's really, really, really important in all these other cases, so it would look it looks, at least it's a prima facie case against a branch counting rule that violates that. Is it more the latter?
You're putting pressure exactly where you ought to be putting pressure. And I think it needs a fuller answer, to be honest with you. But I guess my broad perspective is, in any physical theory, you've got to worry about continuity. I mean, it's just sine qua non. And that goes also for any interpretational structure you'll be putting upon it. It had better be respectful, as it were, of those continuity requirements. So that's a very, very general standpoint. And now on the specifics, that I think fair enough to push, and fair enough that I work out a proper answer in more detail on another occasion.
Absolutely. Okay, no problem. But yeah, this has been very helpful, and I'd love to communicate more about it. And I'm really looking forward to reading the new paper. So, and thanks again for coming.
Thank you.
Thanks, Simon. Our next hand is Lev. Lev, please go ahead.
Thanks, Jacob, and thanks, Jacob, again. And we had a discussion before, and I don't think, and I look again on your paper, and I had the whole talk, and I still don't. For me, it's kind of very strange. The strange is that what you do most of your paper and your talk, you say, let's look on this naive counting rule, and let's play with all kind of different definition of this rule and see which one is stronger to kill it or whatever. The naive counting rule doesn't work. I go to laboratory, I put my Stern-Gerlach close to up-Z, and I don't go equal probability for up-Z and down-Z. So no Everettian would try to look for it. And I think there is no any motivation to look for it. Well, why one would look for naive counting rule? If the words are equal, but the words are not equal. Now, you can say classically, you perform some experiment, or if you put by hand randomness or ignorance, whatever, and you have different outcomes, and then you kind of count, you use this naive counting rule. But you can do this because there is a kind of an assumption that if you don't branch more, then the probability of being in a branch will not happen. The probability will change if you do something, but if you all branches are kind of autonomic, and then you can live with them, and if you don't branch more, then they should be okay. And then you can, in principle, make all branches very similar, and then use symmetry. And quantum mechanics tells you it doesn't work for branching in Everett story. We have amplitudes that whatever you do within branch, provided you do not split it, your weight doesn't change. So there is no any way to make branches equal. They will be always different by their weight, if they're in the beginning different by their weight. Now, if they're not different by their weight, like you agree and Simon agree and everyone, then standard naive counting, it's not naive, and now it works. So, but they're not equal, it should not work. And it's kind of obvious. Well, why to work and look on all kinds of different things to show that it doesn't work? From the beginning, we know it doesn't work. No Everettian will try to make it work. So what is kind of 2/3 of the paper trying something which is obviously wrong, and in different this way is more wrong than the other. Who cares?
Okay, well, I think if you think that all of the branch counting rules are wrong, then probably it's not interesting to argue about which are more wrong. But that's kind of the crux of the disagreement. So when you say, if they're equal, yeah, okay, but they're not equal. They're equal because they have different amplitudes.
Yeah.
Okay, so And I also agree that no Everettian would want to adopt a rule like this, but I think that for me the dialectic is this, and then I agree that I'd say maybe half of the paper probably isn't that interesting to people who really want to cash out the disagreement, or maybe a third or something. But you know, the crux of the disagreement lies about whether, you know, when we're pushed to think about probability in the way that Everettians often think about it, as a matter of self-locating credence, in the idea that we derive the Born rule from some assumptions and talk about whether those assumptions are good assumptions about whether it be rationality, or I think those are maybe not the terms that you'd like to cash them out in, if I understand correctly. But, you know, we're in a position where we're trying to figure out, okay, what in an Everettian universe would I do? Would I care about the amplitudes of these different branches when I'm setting my credences? And the assumptions that we make, I think, about what I should care about, whether I should care about amplitudes, are somewhat distinct from the theory. So when I say, you know, I think that, yeah, of course, the branches are different, they have different amplitudes. Are they different in a respect that matters to me when I'm trying to figure out, okay, how much do I care about the pain of my successors? How much, you know, what kinds of credences should I assign, you know, if I want to obey an exchangeability constraint or something like that? The question is, do those amplitudes matter to me? I think I've tried to give some motivation for the idea that they don't, but of course they're different. I acknowledge they're different. I mean, but the idea that one would say, well, why should we even bother thinking about branch counting? Why should we even bother asking these questions? Because, well, the branches are different. They're different in ways that kind of seem to be relevant to quantum theory. So end of discussion. Well, I think the question is, it's not, are these amplitudes different in ways that just are these amplitudes different in ways that sort of generically matter to quantum theory, but are they different in ways that should matter to us when we're trying to figure out, like, how to maximize utility, how to maximize accuracy, what a priori constraints on my credences I should adopt, things like that. So I think that's where I think it's a worthwhile pursuit.
Let me just, and I think this maybe connects to the literature of decision theory. You put, my question was why you put this original idea of naive counting, and I think the only justification, if you can say that they are kind of equal. And in quantum mechanics, they're equal if you can make them equal amplitude. So at the point, like Deutsch probably was the first to do this, that if you split the words such that all words have equal amplitude. Now, from quantum mechanics, I cannot say they are different, because you can make unitary evolution that makes them all look the same. And then you have a reason to say, now I have to care equally about them because they're really equal. Now, in this moment, branch counting is working. So your original insistence taking seriously branch counting, it works only when there is some equality in branches. And this can happen in quantum mechanics if you artificially make this weights equal. And then everything is fine. So you do have motivation, and you do you know when to consider them equal, when no. If the weights are not equal, of course they're different. And if you have you split them too many into something not important, and then you have just normal counting. You care about your descendants according to their numbers, provided they are equivalent. And then everything seems to be very simple, natural, and works.
So I think so here's the disagreement as I understand it. You said we can only talk about branch counting when there's an equality between the branches. And I say there is an equality. They're not perfectly equal, but there is an equality between high and low amplitude branches. For example, a neutron with a tiny measure of existence feels exactly as one with a high measure of existence. If what I'm doing when I'm choosing what probabilities to assign is doing something like choosing among possible preferences between bets, setting self-locating credences. Those things might matter. Those things might matter to me. If what I, for example, care about is minimizing pain, as classical decision theory says I'm perfectly allowed to do, then there's an equality between those high and low amplitude branches, which at least one can't just assume doesn't matter to me. It might matter. So to say, well, it only works when there's equality between the branches, there's a potentially relevant equality.
But just Sin already answered you about this. He said that this is internal. When you're inside the branch, this is what feels you equal. But for this kind of questions, you have to be outside and think. When you think about probability, you have to think of different branches. So the fact that you feel equally within the branch doesn't help. This is not relevant here. What's relevant is when you're outside. So and outside, the super technology which will try to make interfere different branches will immediately see the difference between small branches and strong branches. But I don't want to take maybe more time.
Yeah, maybe, but we should keep discussing. I had a lot of fun discussing with you last time, and these are good questions. So let's.
The time I'm in New York, so the time no problem with timing. So anytime.
Okay, good.
I have a bit of a follow-up question, but it might be kind of long. So I'm going to bookmark it, and if we have time, I'll come back to it. Jerome, go ahead.
Hey, thank you. That was a really interesting talk. Really enjoyed it. So this is maybe detracting too much from the current discussion, and I apologize, but I'm thinking back to, I think it was slide 16 when you were discussing using the expected utility approach versus just maximizing utility. And you said on the just maximizing kind of utility approach that this might be less appealing on, I think it was a kind of understanding of the metaphysics of branching, according to which there's no genuine fission, but rather maybe I think it's been described as like the divergence picture by Al Wilson versus, like a overlap or kind of fission picture. And I was just curious if you could say more about that and why you think expected utility doesn't sit well with that, or sorry, maximizing utility.
Right. So what this is a really helpful question, and I brushed aside it probably too quickly. My sort of thought was that, I was giving this whole argument about accuracy, and it seems like under certain views of how you think about branching persons, it seems sort of quite natural to think, well, whatever my caring measure is, I should just maximize utility for all my future successors. I was thinking that if you have sort of more of a divergence view, all that I'm trying to figure out is which of these branches am I going to end up on? So it's sort of like, why do I give a crap about all these other people who are having right now very similar experiences to me? I'm just one of them now. So I want to figure out which one I'm going to become. So I don't really care what is the global picture of the, utility across branches, but rather I care about just which branch am I going to end up on, where that I even now is well defined. And there I was thinking that the whole accuracy approach might appeal to you a little bit less. And that's sort of why I also had this very short stuff about exchangeability. That was kind of the thought. I mean, I don't have a extremely well worked out picture about what views about persons will most naturally sit with what, but that was sort of my hunch, and I just wanted to be fair to people who had that kind of view. Does that help?
Yeah, I think that's helpful. I'm still, I guess, even if we have a kind of fission case, I think you might get the same kind of results as the divergence picture, depending on your view of what the persons are. Like if you take a worm view rather than a stage view, well, it could be like, why do I care? I might not know which worm I am on the overlapping view, but and I might share stages with some of these, but I don't care so much about the other ones that I'm not. I'm just uncertain about which one I am. And so I'm wondering if there really is a difference then between the divergence and overlap with respect to maximizing utility.
Right. So I was thinking that sort of the if I'm If I understood you correctly, I was so if I'm currently unsure about which one that I am, oh yeah, so maybe okay, so maybe the thought would be, so is the thought sort of like post branching even on the fission view, I remain uncertain about which I am, and so at that point I'm sort of back in the stage of not so much caring about the global picture, but still again just back to kind of caring only about myself. Is that sort of the idea, or I might be misunderstanding?
Yeah, I'm doing a poor job of articulating this.
You're doing a poor job of
my thought was that there could still be facts about, I guess, who you are in the fission case. And so your preferences could still be about you, as the kind of temporally extended thing.
Good.
Yeah. Even if you at any kind of given time might not be able to differentiate yourself from the other things much like you.
Good. So like the person stages, right. So if you were to take a stage, I'm just a person stage, I'm identical to, and this person stage is all identical, then it doesn't make sense to ask, oh, which one am I, someday going to become? But if you have more of a 4-dimensional worm view, I think that's true. I think you're absolutely right. I think that's where I should have made the division. It's more between, right. It's more between people who think, whether or not you think that there's kind of a well-defined question about which one of these I will become, and that's where the accuracy approach might not work. I think that's a really helpful corrective, and I think that's totally right.
Okay, wonderful. Thank you.
Thanks. Yeah, thanks for that, and thanks for coming.
Thanks, Jerome, and good to see you. Got another hand from Simon. Simon, please go ahead.
Yeah, thanks. I mean, just a general question. I think throughout most of my professional life, the Born rule and the measurement postulate was never really seen as a rule about what rational agents should believe or how they should behave or whatever. And in fact, if only it had been presented like that, it would be a very straightforward case for why the measurement postulates are so unsatisfactory. Since when does it get to be up to a physical theory to tell people what they ought to rationally believe? So I always thought the Born rule really is something about a physical or objective probability. And of course, normal Copenhagen or instrumentalism or something like that has very little to say as to what that objective probability is, and so on and so forth. So where do you stand in what you're trying to do? I mean, would you grant that there's some statistical structure out there in the world independent of anything that we might believe?
Right.
And then there's some issue as to how we form credences. Or because the way you framed, you set up your talk, it seemed to be more that you were looking at what it is reasonable or what it is rational to worry about, as it were, vis-a-vis statistics. But you seem not to care about, well, what actually is the statistics?
Right. So, good. Yeah, I think this is a very that's a really helpful question. So it sort of occurs to me, and it occurs to me even in the way that I formulated your view, was that I even included almost like this postulate about credence, and that isn't really the right way to put it. It's really the right way to put it in that case is that in your view, there is this well-defined notion of frequency across branches. And there you could just take a kind of frequentist or some sort of humane approach to probability in which you say, yeah, it's just there are these physical probabilities. They are also emergent features of reality, but they come from those frequencies. I think that's completely reasonable. What I was thinking was that, there are a lot of, I mean, I think particularly recently there are these, particularly the Everettian approaches where we're trying to show that where it is either about betting preferences or credences, and it is, as you mentioned, not something that should come from the fundamental theory. As you mentioned, what business is it of the physical theory? It's certainly not going to be a postulate of the theory, but can we make some plausible assumptions about rationality or about something like that, in which we get the Born rule? So I think in the beginning, sort of 2/3 of the paper, I was sort of mainly concerned with that. And then I guess I probably should have said, one could really, once we actually get into once we get into the dynamic where it's like branch counting is good, and we understand the probabilities in terms of frequencies across branches, we no longer actually have to think about it in terms of credences. Now we can think about it in terms of these real physical probabilities that are derived from the frequencies. There's also this, I didn't really address at all, like Isaac Wilhelm has his particular view in which you're dealing with kinds of best systems, chances, that are relative to each branch. And I think those are all totally reasonable. I think those are reasonable approaches. I think that the overlap between those who don't want to branch count and I'll put it this way, most people who reject branch counting, as far as I've been able to tell, adopt this more kind of credence or decision theoretic approach. And it's once you introduce branch counting that one gets that we're talking about these real objective physical probabilities. Then one needs, if we want to talk about the link between like credence-based, confirmation theory, one needs something like the principle, but I think we're all happy to say that. Again, the one nugget in all of this that I know of is Isaac Wilhelm's approach, about which I have some thoughts, but probably shouldn't diverge too far from here. But I think that's a very important point, and probably should have been stated a little differently in the paper.
Well, I think you may want to revisit it a bit, because if it's correct, on your view, that indeed there's some statistical structure to the quantum state, and it is what it is, independent of anything that we should believe, well, you've then got another story going about what we ought to care about vis-a-vis epistemology. But that's got to connect up with this thing about, well, what is there actually out there in the world that is this statistical structure? So, yeah, I mean, I just don't quite know how you're going to do that, because it seems to me you've got to perhaps have a mismatch between the two, or you've got to cook up a story about what is the actual objective physical structure, statistical structure out there that matches your more kind of decision theoretically driven view. So I just wonder quite how that goes.
Yeah, that's definitely something I need to think about more. I mean, I think that in terms of I think that if our approach is to look at the statistical structures, if one is still interested in these epistemological questions, they become much more just the normal questions that people outside of foundations of physics are worried about with the principle and with these kinds of things. And it's something where I think one could perfectly reasonably say, not my problem. But yes, I think that's a very good point, and probably it would be worth looking further into into how that distinction.
I mean, sorry, Arthur Jacob, is it okay? Just one little follow-up, if that's all right. I mean, I'm not seeing other hands. So, so your index branch counting, I'm taking that to be something like a rationality, a decision theoretic framework of thinking about statistics. So, so I have my equi-amplitude as an objective structure out there, okay, which has all of these excellent properties, quasi-statistical structure, such as agreement across different ensembles, continuity with the state. The agreement across ensembles is a sort of synchronic consistency condition. So the diachronic one that David Wallace targeted with the naive branch counting rule is sort of similar in a way. But anyway, so I've got my equi-amplitude structure. You've got your decision theoretic structure. Your decision theoretic structure will agree with my equi-amplitude structure. So I think actually what you're giving me is another derivation of the principle.
Right.
Different from Wallace's. So in that spirit, I'm very much welcome your.
Great. See, as contrary to what I said in the at some point in the talk, I am being friendly. And I think it's also I think also the index branch counting as a principle of rationality is something that again, if the right interpretation of the statistical structure is along your lines, I think they work. I think they'll work perfectly fine. And then I think all of the reasons that one might believe index branch counting just from a rationality perspective, I think will carry over. And so it's, it's like either either I've dealt some horrible blow to Everett, I mean, not really, but or I've helping to open the doors to another solution. And
yeah, one of the two. Yeah.
Yeah, right. Right. Yeah, thanks. Those are really helpful.
Thanks, Simon. So we don't have any other hands raised. We've about 10 minutes left, and I have approximately an uncountable infinity of questions. So, but you can't really count them. Yeah, it's it. Okay, so I don't know where to begin with all my questions. I have so many. Probably Jake, you and I will have to talk offline at some point, or online, but not on this line, a different line.
Right. I would love that.
Yeah, so maybe I could start just to sort of lay things out, because I think this will be the crux of many of my questions. It's just how I understand your talk and your paper and what you're trying to do. So let me frame it in a somewhat different way, and you can tell me whether this framing resonates with you or does not. So forgetting about Everettian quantum mechanics for just a moment, suppose I just look at quantum theory in its textbook form from what are usually taken to be the Dirac von Neumann axioms. They're the postulates about Hilbert spaces and density matrices or state vectors and partial traces and all that stuff, the Schrodinger equation, all of it, and then all these measurement axioms, these axioms about what you're supposed to do once you have a density matrix. You have a non-commutative algebra of observables, there's self-adjoint operators on the Hilbert space, and you're supposed to put them together with density matrices under traces, do all this stuff and generate probability predictions and so forth. The problem is that all of the empirical predictions of the textbook theory based on this axiomatic foundation, all of them are just about measurements. They're about measurement outcomes. You have predictions about what outcomes you can get when you measure certain observables, probabilities of measurement outcomes, and all the expectation values, at least on this axiomatic foundation, all of them are statistical averages of measurement outcomes weighted by measurement probabilities. Now, there's a move that many people in physics often do, which is to pretend that those expectation values can be treated like statistical mechanical expectation values, like, averages of stuff really happening. But strictly speaking, that is actually a category mistake. They're not those kinds of expectation values. They're specifically about measurement outcomes weighted by measurement outcome probabilities. So we have a problem. This is ultimately, in a way, just the measurement problem. Either you can somehow, from within the axioms you have, explain what counts as a measurement in some satisfactory, crisp way, and then you're good. And there have been a lot of efforts over many years to somehow get what a measurement is out of decoherence type arguments, just without any additional assumptions. And I think many of the people here are probably in agreement with me that those basically don't work. And that's why we should really do something else. Right. Now, one other thing you could do is attempt to define in a rigorous way what a measurement is at the level of the axioms. But also that doesn't work. No one's been able to find a satisfactory way to add an extra axiom saying, this is what a measurement is. This is the fundamental definition of measurement, and I can put it in the other axioms, and now everything is good. I have all the usual axioms, plus I have an axiom that says what a measurement is. No one's been able to do that either. And people have put a lot of effort into this, and they have not succeeded. So we seem to be stuck, and this is the measurement problem. So another approach that one could imagine doing is just dropping the measurement axioms, keeping the Hilbert space and the state vector or density matrix, the Schrodinger equation, and just dropping the problematic axioms. Now, at first glance, this is going to make our problem harder because now, we have to now also get all of the outputs of those axioms. My understanding of the way that Everettians usually think about this is, well, okay, now what we have to do is somehow derive what would have been in those measurement axioms from the ones that we have. And in a way, this is very challenging. It's a bit like the challenge we had before deriving what a measurement was. We had more axioms. Now we have fewer axioms, and we have to derive, in a sense, even more. And the claim is, can we do this? So one approach is to say, maybe we just need to add some additional axiom, replace the measurement axioms with some axiom that says something like amplitude squareds are to be understood as probabilities in some broader sense than just measurements. Probabilities of things truly happening, like in a statistical mechanical sense of probabilities. Like, these are the probabilities we assign to things actually happening. That turns out to be really hard, just to add like an axiom like that, because you run into all kinds of problems in making it work and making it rigorous. So the other route seems to be, let's not add an axiom like that. Maybe the mathematical Hilbert space axioms alone uniquely pick out amplitude squares as our probability measure. Then we're good. Then we're great. We got rid of the annoying measurement axioms. We don't have to introduce an axiom for measurements. We don't have to introduce an axiom that specifically says amplitude squares to be probabilities, because that's really hard to do in a consistent way. We have our cake and eat it too. From the axioms we have, we uniquely get that amplitude squares are probabilities. If I understand your paper and your talk, what you're basically saying is not so fast. We don't uniquely get that. We could possibly get other things, at least a priori.
Right.
And it's not like you can say, well, but we do experiments. The experiments show that we get the right answer, because if you appeal to experiment, you're not getting them as an output from the axioms.
Right, right.
So what you're basically saying is there isn't a unique answer that the Hilbert space axioms give you for what the probability measure is. And that's what you're basically demonstrating. And so it's not enough to say, well, you know, I don't like your definition of probabilities. They don't agree with experiment. I mean, I think you probably know that they don't agree with experiments, right?
I do, yeah.
Right. So
none of the experiments I've done, yeah.
You're basically, you know, creating a real challenge for Everettians. You're saying, well, you don't want to add another axiom to establish just axiomatically that amplitude squares are going to be probabilities of phenomena happening. And you don't uniquely get that as the output of the other axioms. So you seem to be in an impasse. Do I have basically what you're trying to say?
I think that's perfect. And I think that's it's a much nicer way to put it than I've sometimes put it in the talk and paper, which is, you know, sometimes I think it will sound like, and this is my fault, I'm trying to sort of say, well, the uniquely rational way to assign credences is by index branch counting. That could be, I mean, you could read it that way. I mean, I'm not completely opposed to that, but you know, I think another way of thinking, and this is something that Jeff Barrett really pushed me to say more clearly, was, you know, these are not going to be axioms we add to the theory. They're going to be something like axioms we add to rationality theory, or as Simon has really helpfully been noting, you know, maybe principles about how we understand the statistical structure that are, you know, some could deliver the Born rule, others might not. And so it does sometimes seem that we're at an impasse. I've tried to give some argument that the ones that I'm assuming might look a little bit natural than some of the rationality assumptions that others have used, but ultimately there is going to be some kind of an impasse, and certainly that we're going to have that sort of, I think many will acknowledge, or many will say that yes, we need to add some axioms, not to the theory, but to some axioms to decision theory or something like that, and show that just from the perspective of empirical confirmation, like if these are the bets we're supposed to make, or if these are the credences we're supposed to have, the world would look to us exactly as, you know, the sort of standard quantum mechanics with all these additional probability axioms is supposed to look, says that it will look like. And so I think that probably the most solid way to interpret what I've been up to is to say there are some alternatives. There's some alternatives that, at least on the approaches that most people have given, will definitely not give you the Born rule. And then again, our saving grace, of course, could be Simon.
Simon, we're just about out of time. I'll give you the last word. Please go ahead.
Well, thanks very much. I mean, my question is more towards you, Jacob, actually, because it seems to me if you're going to go the route of, let's look at the structure of Hilbert space, or let's look at, you know, axiomatic frameworks for quantum mechanics and so forth, Gleason's theorem is pretty decisive. You know, if one has a sort of a more formalistic point of view, then I'm not so sure that this is grist to Jacob's mill, really, because he's doing something, and the branch accounting rule you've come up with, Jacob, is
Which Jacob are you talking to?
Yeah, right.
Sorry.
Sorry.
So
Just so
I'm just-
everybody knows, I often, it's my fault because Princeton, the Zoom account always calls me Jacob. I standardly go by Jake. I don't care about either, but if it makes things more, it makes things less confusing, you can call me
Jake has the higher amplitude.
I have-
So we're almost the same, except he's got a higher branch weight.
Even on this branch. Anyway, sorry.
Anyway, but that was just a comment about, as it were, axiomatics. That's all. I think something different is going on in the Everett interpretation. I mean, I think what's going on there is explicit models of concrete states of affairs and how they evolve unitarily and so on and so forth. And whether in that explicit physicalistic model, we see something that a way of understanding probability. And now I think Jake is coming up with, well, there's 2 or 3 different ways of doing it and so forth. So I think it's a bit away from axiomatics. That's all my thought.
All right, we're going to have to leave it there. Thanks, Jake, for a wonderful talk and leading a wonderful Q&A. I now have uncountably infinity -1 questions to ask you, so we'll have to reconvene at some point. But thanks, everybody, for joining us. It was wonderful to see all of you. Have a wonderful week, everybody. Take care. This video will be posted, and I'll send an announcement out soon about our next talk. So
thanks so much, everybody. I would love to keep in touch with all of you to talk more about this and other stuff. So thanks again.
All right, good to see everybody.
Thank you.